might as well let him get started and have more time rather than less. So just quick introduction. So I'm Beth Parks, and I edit the American Journal of Physics. I actually see that Cameron Reed's tuned in. He's the person who actually edited this particular paper. So welcome, Cameron, and thanks for joining. And then Eugene Hecht is the author of the paper that we're discussing tonight, that leads through how it is that Newton eventually came up with the law of gravitation, not fully formed during the pandemic that was going on at that time, but based on work that came about from over the centuries, which I feel very unprepared to talk about in comparison to Gene. So best for me to shut up and let you talk. But I will say, actually, I think he'll talk for a while, maybe longer if he keeps going, but we'll try to have questions. So actually, Mike, is there a way for people to be asking questions as we go by like raising their hand or something?
There is, you can't raise your hand, but you can, there's plenty of room if you want to click start participating in the upper right-hand corner. We will see your video and you can actually raise your actual hand and we will see you. I will also be monitoring the chat. And if there are any questions, you're welcome to type your questions into the chat and I'll read those as they come up during the discussion.
Great. Okay. So Gene, is that okay with you if Mike kind of interrupts with questions that came up from the chat window?
Sure. Absolutely.
Excellent. All right. Well, you are officially introduced and ready to go.
Good. We are going to trace the history of gravity. And we're going to start with Aristotle and run for 2,000 years. So we start with this charming fellow who is both a hero in the saga and a damn nuisance. And you'll see why. We will run from him to my favorite genius of all time, Johannes Kepler. A good man, a nice man, a sweet man. And then we will run the whole gap of the 2,000 years to this fellow, who was very complicated, a bit of a nasty man, a grudge holder. Oh, the stories I could tell you about him. Short-tempered, easily aroused to a hostility, but that's another story. So we got Newton and Aristotle. And the question, of course, is why these people? Why Aristotle? Well, gravity begins really, the discussion of gravity, the concept begins before Aristotle. Things fall, gravity. But Aristotle in the 300 BC era, Aristotle comes up with a theory of almost everything. And because it's almost everything, it's invulnerable to being destroyed. You can pick at it here, you can pick at it there, but it's a theory of the universe. There are 7 planets. There are 7 gods. The planet, planetos, means wanderer. So you have what wanders across the sky. The sun. It's not really a planet, but the sun, the moon, Mercury, Venus, Mars, Jupiter, Saturn, the 7 planets of antiquity. The Earth, of course, is stationary. It's at the center of the universe. It's at the center of Aristotle's universe. The planets, are mounted on spheres, which you cannot see, crystal spheres. They rotate, nested one inside the other, the ultimate mover way beyond on the outer sphere of the stars. So we've got the whole panoply of the universe with the Earth at the center, stationary. as far as motion, things need to be pushed. Nothing moves by itself. Why? Because the universe is a plenum. It's filled with ether, the divine medium. The planets are all divine, unchanging, perfect, from the moon outward. The earth, however, changes. Things rot, decay. Everything moves on circles as they move around as the spheres rotate. The idea of the circles is really from Plato, who was Aristotle's teacher. So we've got ether. It's the fifth element. There are four ordinary elements that comprise everything on the planet: fire, air, earth, and water. You are made of fire, air, earth, and water. You are warm, fire. You are full of fluids, blood, water. You breathe, air, and flesh and bone, earth. Fire, air, earth, water. The thing that's interesting is each of those has a domain. Each of them resides in a place that's natural to them. So Earth resides at the center of the universe, and the center of the universe is the center of the planet. By happenstance, the Earth accreted around the center of the universe. Water in the sphere above, air and fire beyond. So everything has its place. The rest of the universe is a plenum filled with divine ether. Now, this story, which is, of course, somewhat silly, is passed on by good fortune. And by that I mean Aristotle was the teacher of a young man named Alexander of Macedon. And Alexander was a tough young man who took the Macedonian armies and swept across all of Greece and into Persia and across Persia down to Egypt and set up a city called Alexandria, which is of great significance to this particular story, and then all the ways across to India. So the empire, Alexander's empire, all across which Aristotle's physics, Aristotle's astronomy, Aristotle's science was taught. The physics is essentially that everything is moving through a medium and so has to be pushed. You stop pushing, it stops moving. If there were a vacuum, then something would go forever all by itself in a straight line at a constant speed. And that's ludicrous. Funny, isn't it? So you have to push everything. Things fall in proportion to their weight. And that is the doctrine which is central in Alexandria. It's taught in Byzantium, Constantinople. Ultimately, the Greek Empire collapses, not very big to begin with. It collapses, the Romans take over, the Romans save Greek science, Greek medicine, Greek astronomy, and then they in turn collapse. The Muslims pick up Aristotle, they take over Alexandria, and they take everything across to Spain. So now we have Aristotle, many of the Greek philosophers being taught while Europe is in the Dark Ages. There is a fellow who comes along in 100 AD named Claudius Ptolemaeus. He's working in Alexandria. He's a Greek philosopher. And he takes Aristotle's ideas and mathematizes them. So instead of just having the spheres, he's going to mathematize the system so that it has predictive power. And in order to do that, he has the planets move on circles. And then those circles move on other circles. And the centers of the circles are shifted. And if you add enough variables, you can spell Coca-Cola in the sky. And what he does is I even saw somebody who put together circles on top of circles on top of circles and made the planet move in a square. It's hard to believe, but back to Ptolemy. So Ptolemy constructs this fantastic system predicated on Aristotle that has wonderful predictive powers. And it's a good thing to think about that our modern planetaria, if that's the plural for planetarium, operate with gears on top of gears in essentially Ptolemy's system. Fun thing to think of. Well, after Ptolemy, the next and probably the last great Greek scientist is a man named John Philoponus, John the Grammarian, 400 AD. John doesn't like Aristotle's nonsense. He doesn't like the idea that Aristotle said things fall in proportion to their weight. He says, drop two things and watch them. Drop a cannonball and drop a bean. They will fall nearly the same. So Aristotle's idea about falling things is nonsense. Aristotle said things had to be pushed. So if you throw a ball, how come it keeps going? Aristotle, excuse me, very cleverly says the air moves behind to fill the vacuum. As the ball moves, it creates a vacuum. The air moves behind it and pushes the ball. Wonderful nonsense. But it's reasonable. Everything Aristotle's a cunning guy. He can explain anything, and that's the trouble. So for 1,000 years, there are scholastic scholars who believe everything Aristotle says. In any event, Philoponus says, no, it isn't air rushing back. It is that the person who throws the ball imparts to it a motive power that stays with the ball and the ball continues to move. And that's the first breath of the law of inertia. It will be modified as time goes on. So that's our friend Philoponus. That's the late 400s. The next person to come on the scene and do something extraordinary is a fellow named Jean Buridan. He's in the 1200s, the late 1200s. He's teaching at the University of Paris. He picks up on Philoponus's story and he says, okay, there is a motive force, a motive power that the thrower imparts to the projectile. And the measure of that, and let's call it impetus, the measure of that impetus is speed and something else, speed and another thing that was contributed by one previous scholar who lived just a few minutes before our friend Buridan, and that's Aegidius Romanus. Aegidius had gone to Rome, so he tacked his name Romanus. Aegidius Romanus has a problem. He is a churchman. He's teaching at the University of Paris. There were already universities in the 1200s. He knows all about Aristotle. He's an Aristotelian. But he has an issue. The church has said that literally the body of Christ is the bread. The blood of Christ is literally the wine. How could that be? The weight is different. The volume is different. How could it be? There must be something that is conserved. Guess what? The quantity of matter in the body is in the bread. The quantity of matter is conserved. That's one of the first conservation laws, 1200. So, quantity of matter, in particular in relationship to the transubstantiation, but the philosophers very quickly pick up on it. And they say perhaps the quantity of matter of everything is conserved. Because if you took, I don't know, an apple and squashed it, you still have an apple. The quantity of matter is the same. If you chop it up, the quantity of matter is the same. If you, etc., etc., etc. Maybe the quantity of matter of everything is conserved. Very appealing idea. And now Buridan, who's almost a contemporary, a few years later, Buridan picks up on this and he says, the true measure of motion that results from this impetus, the true measure of motion is this. And what is this? This is quantity of matter times speed. A cannonball made of wood and a cannonball made of iron fired at the same speed, what will happen? The iron ball will blow up the castle, the wooden will bounce off the walls. Why? Because it does not have the same impetus. Mass times speed. But he doesn't say mass yet. Quantity of matter times speed. And what is that? Momentum. And momentum is born. This is the 1200s. Momentum is born. Another 200 years and we have Copernicus. Now, it's always said that Copernicus is the fellow who brings in the scientific revolution. But Copernicus is a sweet, nice man. He doesn't want to have a revolution. His book, The Revolutions of the Heavenly Spheres, in 6 volumes, he didn't even want to publish. He was afraid he'd be criticized. So his assistant, Rheticus, makes sure that it gets published. In fact, it only gets published and put in Copernicus's hands when he's on his deathbed. That's how hesitant he was to have this thing published. In any event, what Copernicus wants to do is he wants to replace Ptolemy's picture with circular orbits where the planets move at constant speeds. He feels that that's the centerpiece. That's back to Plato. So he renegotiates Ptolemy's picture. He puts the sun more or less at the center, not really at the center. What's at the center of the universe is the center of the Earth's orbit. The Earth is now roughly orbiting the sun. Then you have the moon, Mercury, Venus, Mars, Jupiter, and Saturn. Revolutionary. The word revolution comes from his book, incidentally. It was never used before, The Revolutions of the Heavenly Spheres. So Copernicus now passes away. The book is out there and everyone pays no attention to it. It's very good at predicting, but it doesn't predict any better than Ptolemy. And you have to then accept the fact that the Earth is no longer at the center. By now, heaven surrounded the planets. The Earth was at the center. Hell was inside. Dante had given us the 7 rings of hell for the 7 planets. Everything was understood. And now you're going to yank the Earth away from the center where we've always loved it. We're at the center of the universe. No one wanted to play. So Copernicus got very little attention. He was, however, adopted. His ideas were adopted by a handful of people. One of them was a fellow named Michael Maestlin. He taught at Tübingen University in Deutschland. And along comes a fellow named Johannes Kepler. He goes to the university. He's going to be a churchman. He's going to be a pastor. This is a Lutheran college. He's a Lutheran, very religious man, and he's going to be a preacher. He meets Maestlin. He's totally enraptured with Copernicus's theory because he loves the idea of the fireball of the earth, of the sun rather, the fireball of the sun driving the planets around it. It's a lovely picture. He's swept away with it, but he still wants to be a preacher. The university, however, has different plans for him. Either they're annoyed with him because he was a pain in the ass. He kept giving lectures on Copernicus. He kept doing things. He bothered them, but perhaps they recognized that he was something of a genius. In any event, they say to him, "You're leaving, buddy. You're going to take a job at Gatz." It's something of a high school, really, more a high school than anything else, a Lutheran school. You're going to go there and you're going to be the professor of math - astronomy. And he says, "I don't want to go. I don't know anything about astronomy. I hardly know any mathematics. I don't want to go." "You go." He went. And after a couple of years, he gets more and more involved in the teaching of astronomy and the teaching of mathematics. And he actually has the arrogance to write a book. He writes the first book, and it does take some arrogance, I can tell you, having written a couple. You got to be a little cocky or a little young, cocky. Well, he wrote The Mysteries of the Universe, Mysterium Cosmographicum, the mystery of the cosmos. And in it, you can see the genius at work. For the first time, he's saying, why do the planets move? No one had ever asked. God made them. God put them up there. The angels moved them. Everything was understood. He's saying, why do they move? How do they move? They have a inertia, a resistance to motion, not a resistance to changes in motion, which is what we call inertia, but just a resistance to motion. That's the beginning. He names it inertia. That's where the word comes from. So they are pushed. He's an Aristotelian. The planets must be pushed because they have inertia. Well, if they're pushed, what's pushing them? It must be a force. That's the first time in all of history that anyone said anything about forces moving the planets. Well, the planets don't seem to move uniformly. As you look at them farther and farther away, they're going slower and slower. It must be that the force drops off with distance. Amazing. He's saying mathematical things about forces. No one ever did that before. They were the angels pushing. Who thought of 1 over r, 1 over r squared, the force dropping off with distance? Well, first he starts thinking, well, I'm getting ahead of the story by 3 or 4 years. In any event, he's already thinking of forces pushing the planets in his first book. Now, since he had to pay for it to be printed, he had 200 copies available, so he sent them all over the place. Any royalty who he knew who was interested got one. A gentleman a famous astronomer by name of Tigre Otessen Bra. Tycho gets a copy of Mysterium. Galileo gets a copy of Mysterium. Everybody gets a copy. He's got, as I say, 200 copies to unload. Tycho needs someone to work on his theory that the Earth is at the center, but everything else goes around the sun, the Tychonic system. And he figures this young German who can calculate, makes all sorts of calculations, I'll get him to work for me. I'll feed him, I'll dribble my data to him. Kepler goes, he's under pressure. He's a Lutheran. The 30 Years' War is raging. He's being pushed from one country to another. He's under all sorts of pressure. He gets an invitation from Tycho, come and join me in Prague. Tycho was in Denmark, but he offended the king. He was a real arrogant. I don't know if you know anything about Tycho. He was an arrogant, aristocratic gentleman with a silver nose. He had his nose chopped off in a duel. He wore it tied around the back of his head, and he was miserable. The king of Denmark gave him the island of Uraniborg and a castle on it to do his observations. Why? Because one night he was going home from his uncle Steen's. There's a question of whether it was a laboratory where he was doing alchemy or whether it was a bar and grill. But in any event, he sees a star that didn't belong there. It wasn't there yesterday. It was a supernova. And Tycho publishes a book, De Stella Nova, the new star. And he becomes famous. The king of Denmark loves the idea, gives him the island, gives him a castle, Uraniborg, and Tycho, for the rest of his life, takes miraculous data. He is the last naked eye, I love the phrase, naked eye astronomer. He builds gigantic sighting devices. He's endlessly patient, and he accumulates an incredible font of data, much of it on Mars, which is lucky because Mars has an elongated orbit, and Kepler will discover the elliptic nature of the orbit because he has all this data on Mars. So it's very fortunate. Tycho invites him to come. He's now in Prague because he didn't get thrown out. He left. He had a fight with the king of Denmark, and he got an offer to go to Prague and work for Rudolph II, Emperor of the Holy Roman Empire, and a complete wacko. He changed his birth date because he didn't like the astrological notion of the real day. He was quite a character, art collector. I could talk to you 20 minutes on Rudolph. In any event, Kepler joins Tycho. They give him the job of working out the details of the orbit of Mars. He fights with Tycho because he wants all of Tycho's data. He wants to prove Copernicus is right. Tycho dribbles the data. Tycho wants to prove that Tycho is right. This tension goes on for almost a year, and Tycho dies. There are stories. There's one story, which I love, may not be true, that he drank. He was having a party. He drank to the king. Then he drank again. Then he drank to the queen. Then he drank again. And his bladder burst. And he was in agony for 2 weeks and died. In any event, Tycho's out of the picture. Kepler is now bequeathed all the data, which actually he steals. He steals Tycho's data. And he gets chased by Tycho's son-in-law, but that's another story. The Emperor Rudolph needs an astrologer. Kepler is an astrologer. He's been an astrologer-astronomer for years. He gets hired to replace Tycho at a much reduced salary. He is now the imperial mathematicus, the imperial mathematician. And that's such a highly honored position that he will, for the next 12 years, work in Prague, be recognized all over the, I shouldn't say all over the world, because Asia, ultimately his stuff goes to China. But in the beginning, he is a figure on the landscape. He is the imperial mathematicus. He works on the data. And as all of you know, he publishes 3 laws, the 3 planetary laws. What is not altogether common knowledge is he discovers the second law, a line drawn from the sun to any planet sweeps out equal areas in equal times. He discovers that law first. And it isn't by just screwing around with data. It is by manipulating his theory of how the planets are moving. What makes the planets move? Now we come to an interesting juncture. His theory of planetary motion. He's got 2 jobs he wants to do. He wants to prove that Copernicus is right, that the sun is spinning and hustling the planets around. The sun is sweeping the planets with a sweeping force. The force grabs hold. It literally lays hold of the planet and moves it in its orbit. He's an Aristotelian. Something has to be pushing the planets. It is this prehensile force. That's what he called it. But if Copernicus is right, and now here's the centerpiece for this story, if Copernicus is right, then Aristotle is wrong. The Earth cannot be the center of the universe, it's a planet. And if the Earth is not the center of the universe, then pray, what is gravity? Why do things fall? They can't be falling to the center of the universe. They're falling to the center of the Earth, which is now orbiting. So he's got to come up with a gravitational theory that explains all of this, and then he's got to come up with a planetary theory. Well, his planetary theory is all nonsense because he doesn't have enough physics. He has read William Gilbert's De Magnete. Gilbert was Queen Elizabeth I's doctor in 1601. He publishes De Magnete. First, well, not really the first, but the most recent analysis of magnetism. Very, very cutting edge, very, very modern. And in it, he says, the Earth is a magnet. There is a magnet in the center of the Earth. And this tickles Kepler, because if the Earth is magnetic, then maybe magnetic forces move the Earth. Maybe all the planets are magnetic. Maybe the sun is magnetic. Maybe magnetism is sweeping the planets along. Maybe the prehensile force is a magnetic force that drops off with distance. Magnetism drops off with distance. Now, he discovers all the planes of the orbits pass through the sun, and they're all very close to each other. So maybe this force, instead of, and this is what he thought of first, he thought first that the sweeping force spreads out into space in all directions like light from the sun, in which case it would drop off 1/r squared. But now, since all the planets are in pretty much the same plane, maybe they're all swept in the plane. Maybe the sweeping force goes as 1/r, increases as circles, as the circumference of a circle, not decreasing as a sphere. So he finally decides his sweeping force drops off 1/r, not 1/r squared, but he considers 1/r squared. That's important because, of course, it will go all the ways to Hooke and ultimately to Newton. So, what about gravity? He's got magnetism pushing the planets. They're moving in elliptical orbits. He's got them all figured out, he thinks. Magnetic forces, the sun must be turning. If the sun is turning, shouldn't we see it turn? And within a couple of years, Galileo announces the sun is spinning. Now, there's a wonderful thing as you teach. There's a totally wrong theory making a totally correct prediction, and Galileo observes it, and Kepler feels, okay, I'm on the right track. Now he's got to settle gravity. Now, Kepler's a smart man. He says nothing is falling to a point. Nothing could fall to a point. That's silly. Aristotle's conclusion is nonsense. It must be falling to a thing, the Earth. The Earth is drawing on stuff. Stuff falls because the Earth pulls it, and it pulls the Earth. Gravity is a mutual attraction between objects. And what are the objects? The objects have quantity of matter. Now, there's a little issue here. By the time Kepler comes to say this, the church is not going to allow it. The church, the Inquisition is here. They burn Bruno at the stake. They're not tolerating anything. The Protestants have come, and with the Protestants threatening them, they formalize everything. They formalize the transubstantiation, and they look very much askance at anybody who's going to say quantity of matter. That has to do with the transubstantiation, and you nonsensical astronomers can't use the term. So Kepler invents a term of his own. Moles, the Latin for mass, the Latin for a lump, an amount of stuff. And now he uses it and says it is conserved. The planets have moles, mass. And he is the first one to say gravity arises from mass. And he's the first one to say inertia is proportional to the mass of the object being pushed. He invents inertial mass and gravitational mass, not Newton, Kepler. In his next book, Astronomia Nova, he publishes the true doctrine of gravity. And the true doctrine of gravity is that if there are two objects far away from a third object that might interfere, far from the sphere of influence of a third object, gravitational sphere of influence. My God, I could read it, but I have a couple of paragraphs I thought I'd read, but I'm babbling on forever, so I won't read any of it. But he says, if you have two objects in space, they will come together traveling distances which are inversely proportional to their masses. They mutually attract. If they are far from the sphere of influence of a third body, he's nailed the whole damn picture. Amazing. And this is just at the turn of the 1600s. It's 50, 60 years before Newton is born. Kepler is saying gravity is the mutual interaction between two masses. It's proportional to the masses. He doesn't have the third law. He doesn't have Newton's third law, that the forces are equal and opposite. He thinks the proportion, he's really not clear on it, but it looks like. He thinks the little guy gets a big force because the big guy pulls him harder, and vice versa. But he then sits down, and this knocked me out. It knocked me out for two reasons. It cost me a good penny to get it translated because it's still in Latin, and my Latin is terrible. I hired two translators to make sure I got this paragraph right. And one made chop suey out of it. One was a disaster because it's Old English, it's Old Latin, and it's physics. The other guy got close enough so that my impaired Latin could make sense of it. He actually calculated the point between the Earth and the moon where gravity would be canceled. This is amazing. Before Newton, before Hooke, before all those dudes that we always think of as being the fathers of gravitational theory, he calculates where the point is, where the force of gravity from the Earth cancels the force of gravity from the moon. He gets it wrong because he thinks it's 1 over r instead of 1 over r squared. But boy, that's a hell of a calculation.
Eugene, since you paused, can I ask you a question there?
Joe, please.
Because I'm really curious about this idea of understanding gravity, or thinking that gravity exists, but not thinking that it's required for celestial motion, and yet having worked out this thing that's obviously celestial for where gravity would be zero between the Earth and the moon. I don't understand that.
Yes, wonderful, wonderful question. Wonderful question, because Kepler has kept gravity separate from astronomy. His celestial mechanics is totally separate and total nonsense. And his gravity is superb. The man has incredible insights, and he has audacity. This is 1600, 1610. It's utterly amazing. Now, what he does say that's perfect for your question, he says the earth pulls on the moon, and the moon pulls on the earth, and the moon pulls on the waters of the earth, because the waters of the earth are kindred to the matter of the moon, and gravity is between kindred entities. So the earth pulls the moon pulls the earth, the moon raises the tides, the earth, being bigger and more powerful, holds the moon and even goes farther. And for that, I will read you something that you will love. I'm glad you asked. Catch this. Nothing that consists to any extent whatever of terrestrial material carried up on high ever escapes the grip of this mighty power, gravity. The earth will not allow anything carried on high to ever escape. Well, of course, he doesn't know anything about the escape velocity, but boy, this is 60 years before Newton is conceived, and he's spelling this stuff out. I always found it breathtaking. Kepler is just miraculous. So to summarize Kepler, forget his planetary theory, keep his three laws. Planets move in elliptical orbits. Line from the planet to the sun sweeps out equal areas in equal times. And the last one, the period is proportional to the 3/2 power of the semi-major axis. That will be what Newton uses to get that gravity varies inversely with the square of the distance, off in the future. Now Kepler dies. He's decided gravity is mutual between masses, proportional to the masses. It drops off 1/r. And then in his last book, which is published after he dies, it's called Somnium, which is dream. It's a science fiction story. It's a science fiction story of a magician carrying someone off to the moon, a trip to the moon. And he describes all sorts of things. But that description is, he wants to make sure people don't misunderstand the physics. So he puts notes. There are over 200 notes accompanying this short science fiction story. And in one of the notes, he says, for the first time, that the sun and the moon affect the tides. Now, they had suspected that the moon and the sun perhaps somehow were affecting tides. But he says the sun and the moon affect the tides gravitationally. Wow, that says that the sun interacts with the moon and therefore must be kindred stuff. But the moon is kindred with the earth because the moon affects the earth and the tides. So the sun, the earth, and the moon all affect each other gravitationally. This is the last years of his life. He ain't going to go back and redo his magnetic nonsense of pushing the planets. So he leaves it to the reader and says no more. But now the sun, the moon, the earth are gravitationally interacting. It's a short hop to make the rest of the planets gravitationally interact. And that short hop, and I'm going to cut to the chase because I see some of you are falling asleep. there comes a fellow named Horox, Jeremiah Horox. The thing about Jeremiah Horox is that he's only in his 20s. He's a reverend. He's in England. He's fascinated by Kepler's, excuse me, Kepler's celestial mechanics. He wants to apply Kepler's physics to the universe. He doesn't like the idea of magnetism pushing the planets, so he says, essentially, the magnetism, the sun's magnetism, and when he says magnetism, he really means gravity, because at this point in time, everybody is wondering whether magnetism is the same as gravity. Kepler's theory that magnetism was pushing the planets has already begun to metamorphose into gravity interacting with the planets. So Horox says the sun gravitationally with its magnetism, but really gravity, only attracts the planets, only attracts and draws the planets, and they behave like projectiles. The impetus makes them move in a straight line, but a projectile moving in a straight line falls by gravity. It must be that the planets going in a straight line fall towards the sun. He's anticipating Newton. So now the sun is interacting gravitationally. And then he goes a step farther and he says, Jupiter, which is leading Saturn, he already has a telescope, incidentally, no more naked eye. He's watching Jupiter and Saturn with a telescope, and he concludes that Jupiter has been slowing down for the last 150 years, and Saturn has been speeding up for the last 150 years. Now, what the hell is going on? Well, Jupiter's leading Saturn, and Saturn is pulling Jupiter back and slowing it, and Jupiter is pulling Saturn forward and speeding it up. And in another couple of dozen years, Halley will observe this and come to the same conclusion. So now gravity is interacting between Jupiter and Saturn. And if I thought you could stand very much more of this, I'd trace it through Bellini and Gassendi and a half dozen other dudes who pick up on mass and use moles. Torricelli, who's Galileo's assistant, of course, everybody knows Torricelli. Torricelli read, he says, almost everything Kepler wrote. He's a follower of Kepler. He uses moles to mean mass. There's a dozen Italians. The whole Italian school is afraid to use quantity of matter because Galileo's just been put through hell by the Inquisition. They're never going to utter the words quantity of matter, quantitas materia. So they say moles. They follow Kepler. So a dozen guys for the next 50, 60 years are using Kepler's idea of mass. Kepler's gravity has already blossomed and replaced his magnetic nonsense. Roberville, Frenchman, says the universe has the sun at the center. The place is filled with ether. The ether thins as you go out. The planets float at the different densities of the ether. The sun is blowing them out. Gravity is pulling them in, and there's a balance. there's an equilibrium. Unfortunately, they don't know anything about centripetal force. They think it's centrifugal. But that will be straightened out in time. Huygens will deal with it, but he never gets it straight. He writes v square over r for the centripetal acceleration, but he thinks it's a centrifugal force. Newton does as well. Newton, when he's a young man, comes up with v square over r for the centrifugal force. And only just before he writes the Principia does he realize it's the pull inward. It's the pull that pulls the planets off their inertial paths. Now, I can go on forever. So if you have any questions, go to it. The piece that I'd love to tell you about is Newton's shtick, how Newton screwed Kepler, if you want to hear it. Yeah? Mike is shaking his head, yes. Harry is shaking his head, yes.
Could I ask a question?
Hello?
Could I ask a question?
Of course.
Okay. Where would the moon, being 60 times the Earth's radius and the 9.8, when you compare that with the v square over r, the 1 over 3,600, does that fit in anywhere historically in this to get the inverse square law by the ratio of the two accelerations?
The way they got the inverse square law was first they had to have centripetal. Once they got centripetal, they had the force holding the planet in orbit was proportional to v square over r. Now you take Kepler's third law, which says the period squared is proportional to the cube of the radius, and the period is the 2 pi r once around. If you divide that by the speed, you get the period. So you got the speed, which is v square over r. You combine v square over r with Kepler's third law, and you get that the centripetal force must be 1 over r squared, must be proportional to 1 over r squared. Newton did that. Christopher Wren did it before Newton did it. Newton knew Wren did it. He even says so in a letter to Haley. Haley says he figured it out, that the force must be 1 over r squared by equating the centripetal to manipulating Kepler's third law. And you combine them and you get that the force, the centripetal force, must be 1 over r squared. Hooke guessed it. Hooke guessed it by saying light spreads out in all directions, gravity must spread out in all directions, it must drop off like light, it must drop off as 1 over r squared. He never did the math. Hooke was not much of a mathematician. He was a brilliant thinker. He guessed all sorts of stuff. He came up with the universality of gravity before Newton. Hooke was lecturing on all the planets interacting gravitationally. Hooke knew Kepler's work and even quotes Kepler. Newton, if you'll excuse the expression, was something of a nasty guy. And he didn't want to be dependent on anybody who was traceable. He could give credit to Galileo for stuff Galileo didn't do, and he did that in the Principia. But he wouldn't give Kepler credit for gravity. He gives him credit for all sorts of things before he actually publishes the Principia. In his early writings in the 1680s, before the Principia, he says this is what Kepler did. Kepler, the third law, Kepler, the first law, the second law, the third law. He knew all of it. But when you read the Principia, he treats Kepler like he never heard of the name. In fact, two guys, Maclaurin, who was a student of Newton's, and Gregory, who was also a student, not student, they followed Newton around. Both of them wrote books after the Principia, and both said Kepler was responsible for all this work on gravity. Kepler's true doctrine of gravity. They both talk about it. Newton never mentions it. Never mentions it. Never mentions that Kepler started the idea of inertia. Never mentions that Kepler started the idea of mass. When it came to mass, and Torricelli and Bellini and a whole bunch of people used moles, Kepler's mass. Newton goes ahead and uses a different word for mass. He uses massa, which is another Latin phrase for a lump. So when Newton, who we say invents the idea of mass, he was just hiding the fact that Kepler had done it before him. I don't know, that probably goes well beyond what you asked.
So the numerical 9.8 meters per second squared, this comes later then.
Much later.
Okay.
Much later. Cavendish takes a torsion balance and measures the force between two known masses. And from that, he arrives at what he wanted, which was the mass of the Earth. He does not come up with a value for G. That's later. When the final equation is formulated, F equals GMM over R squared, that G is a late 1800s value that a number of skillful people were able to measure. So G doesn't enter the equation. In fact, I have never found a book in English until 1909 that has the equation F equals GMM over R squared. There is a book that has F equals little f mm over R squared, but G, the universal gravitational constant, that doesn't appear in English until the 20th century, which surprised me.
Can I throw in a question?
I wish you would.
I was struck by what you said with Horox and Jupiter and Saturn mutually attracting. And I think I recall reading that Newton was motivated to introduce the third law to properly explain the orbit of the moon. And I was just wondering, do we know anything about the history of, maybe I'm wrong on that, of the origin of the third law?
The origin of the third law. Kepler, I hate to schlep you back to Kepler, but Kepler said, when you pull on something, does it not pull back? The sun pulls, it claws on the planet. Does not the planet claw back on the sun? He does this in his book, which has a lovely pronunciation, Epitome, the epitome of Copernican. It's a digest of Copernican theory that he wrote over a series of years. It's a textbook that asks a question and then explains it, and asks another and explains it. And one of the questions is, does not A stick pulled back on you when you pull on it does not action reaction. Now, he doesn't ever say they're equal and opposite. That, I think, is Newton. I think Newton adds that. But everybody knew that if you pull on something, it pulls back. That much was common knowledge. As far as I can tell, Newton's the first one to actually lay it out as the third law. I've often thought if I live long enough, I'll chase it and chase the idea and see if anybody else said anything about it. But it is an interesting idea. And you know what he did? Oh, you'll love this. Newton says essentially, here's a mass, here's a different mass. They pull on each other, are the forces equal and opposite? Suppose that we put a piece of paper between them. He doesn't say paper, he says put a thing between them. If the force is not equal and opposite, what happens? Away it goes. It accelerates. It has to accelerate. There'll be a net force on it, and it will accelerate forever. And since it cannot accelerate forever, that would be ludicrous. It cannot be that the forces are unequal. They must pull on each other. So that's in the Principia. But it's been pointed out by historians that he generalizes that to the force on the moon. The Earth pulls on the moon pulls on the Earth, and they're equal and opposite. He's got no basis for that experimentally. That's off the top of his head. That's a generalization from this one. But it's charming. I love that thing. Fun? So Newton ends up screwing Kepler. That's the moral of this story. And the guy who actually wrote F equals ma first, Newton never wrote it. The guy who wrote it was another brilliant guy named Hermann, Jacob Hermann, who lived a few decades at the end of Newton's life and onward. Jacob Hermann was the first to really set out F equals ma, and he gave Kepler credit for the law of inertia. So the point is, everybody knew that Kepler was a genius, that he had done all this magical work. But if you read the Principia, he says second-rate nothing. He came up with, he did the first and second laws. Everybody knew them. And you wonder, why was Newton playing Kepler's contribution down so aggressively? And the only answer that you get is, in that era, people felt their work, in order to be great, had to be original. There is a treatise that goes into this originality business. The work had to be original to be memorable. And if he allowed Kepler to have said gravity depended on the masses and dropped off with the distance, and it might even drop off in verse with the square, then what did you do, Newton? Well, of course, Newton's the genius who mathematically puts it all together. And without him, there wouldn't have been anything. But without Kepler, there wouldn't have been Newton. If Kepler didn't do, and forget the three laws, that's all he's known for nowadays is the three planetary laws. Forget the planetary laws. If Newton didn't have Kepler to stand on and not mention, he could never have written the Principia. Never. Wouldn't have had the law of inertia, wouldn't have had gravity, wouldn't have had anything. So that's the moral of the tale. How we doing up there, kids?
was assuming that some of the new people who joined have a question to ask, which I let you just sneak in on, and then I'm gonna like call time pretty soon. But if Cameron or Raymond, if you guys had questions.
Whatever you guys like.
Was there any thought of how long it would take for these forces to interact with each other? Did anyone think that if you put two masses, how long does it take for the one mass to know the other mass is there?
That's a fun thing that we never teach. We write down F equals G mm over R squared, and off we go. Instantaneously. It was all instantaneous, which is, of course, not general relativity, not special relativity, not anybody's relativity. No, gravity was instantaneous as far as Newton was concerned. But Newton hated the idea of action at a distance. Hated it, and wrote that he hated it. Couldn't possibly be action at a distance. Kepler didn't give a damn. Kepler said it was action at a distance. In fact, Galileo published in one of his books a scathing remark that Kepler's theory was totally inappropriate because gravity can't do this. This is action at a distance. No. And Newton didn't like it one bit. He said, there was a force, you have to deal with it, but it can't possibly be action at a distance. And yet, of course, it was. Leibniz called Newton, hated the whole thing that Newton came up with because of action at a distance. And that wasn't settled until Einstein cocks up the four-dimensional space-time and uses that as a medium for action at a distance. The sun distorts space-time. The Earth flies through distorted space-time. Everything is just perfect. You don't have to worry about there are no gravitational forces in general relativity. He gets rid of gravitational force altogether. It's just distorted space-time. And you fly like a roller coaster. Now, how the hell you interpret two lead balls attracting each other if there is no gravitational force, I do not know. What are they? Well, that's another story.
Yeah.
We make this shit up, kids.
I'd like to read a question from the chat from JDeep.
Sure.
Actually, two questions and a PS. Number one, how much of Aristotle's theories are based on empirical evidence? Number two, what should we be telling our students about Kepler? And the PS, thanks for your wonderful optics book.
That's kind. So what was the first one? What was the first question?
How much of Aristotle's theories are based on empirical evidence?
Oh, he was not committed to worrying about evidence. If he had been, he would have done Philoponus's experiment and dropped a pea and a cannonball. He couldn't have dropped the cannonball, of course, for another 1,300 years, but he would have dropped a big rock and a little rock and seen that they don't fall at the same speed. That would have been obvious. So Aristotle was a genius. He did the best he could. He fudged as much as possible. He rationalized, and he came up with a glorious picture that dominated thought throughout the Middle Ages. He gives it in 300 BC, and it isn't attacked for 1,000 years. It's incredible. And it isn't totally overturned because Kepler is using parts of it. Galileo is using parts of it. And impetus theory derives in part from the idea that you needed a force to keep things moving. It's only when you finally liberate and the full law of inertia says a thing goes all by itself that you finally get away from Aristotle. So empirical, not much, if anything. But of course, nobody was doing empirical until you get to Archimedes. Archimedes is the one who brings science into some sort of observational experience, not long after Aristotle. What was his second piece?
Okay, second question. What should we be telling our students about Kepler?
You should tell your students that the theory of gravity begins with Kepler. That Kepler, because if the Earth is a planet, things cannot fall to the center of the universe if the Earth is moving, because the Earth is then no longer the center of the universe. So gravity is an attraction, a mutual attraction between kindred objects, stuff. And that's good enough. That'll get you to the Newton, to the lap of Isaac Newton. Any more questions?
I got one. I recall reading that Galileo had pretty much figured out what would be equivalent to law of inertia. And based on what you said earlier, there was the communication between Galileo and Kepler. Do you have any idea, did Kepler come up with it, or did Galileo come up with it independently, or was it the influence of Kepler's writing?
You have to be careful. Kepler said that inertia was the resistance to motion. That's not what Galileo was playing with. Galileo was playing with the constancy of speed. That leads to acceleration. If you're going to have acceleration, you need force. To change motion, you need force. So the law of inertia is body in motion tends to stay in motion, as well you know. Mm-hmm. Galileo did not contribute anything really of substance to gravity theory, because he was, in that regard, an Aristotelian. What he did do was he rolled balls down an incline. And then he was clever enough to put another incline like this. So he puts a ball there, rolls down and rolls up, and it almost goes to the same height. So he says, there's something going on here. So he polishes the runway, and the ball goes up a little higher. Then he covers the runway with parchment and polishes that, and the ball goes almost to the height that it started at. So he says, things will seek their own heights. They fall the same heights. So now he takes the second ramp and lowers it. And it becomes longer, and the ball goes almost to the same height. Then he lowers it, and it goes, way the hell down, almost to the, and then he lowers it horizontal. And he says the ball will roll forever. A body in motion will stay in motion forever. But then he gets lost. And he says, it must be following, this is very cool, it must be following the curvature of the Earth. So the ball wants to go forever in a circle. So inertia is not linear, it's circular. A body in motion will stay in motion in a circle forever, which he proves experimentally. And now he understands the planets. All the planets move in circular orbits because of their inertia. There are other people who straighten it out. And miserable Descartes is the guy who finally straightens it out. Descartes was miserable. He stole from everybody he could. Splendid mathematician, marginal philosopher, crappy physicist. He stole from Beckman. I'll tell you this just for a minute. Beekman is a genius. He's working in Holland. Descartes is a soldier. He's in Holland. He meets Beekman. Beekman takes him under his wing. Beekman is a mature man. Descartes is a young soldier. Descartes is a mathematician. They work on little mathematics things together. Beekman lets Descartes see his notebooks. Descartes steals everything that's in Beekman's notebooks. Descartes publishes it. When Beekman writes to him and says, Descartes, I want to publish my stuff, Descartes writes back, no, don't publish that. No, I've already published this. You cannot do that. And Beekman's such a sweetheart, he never publishes it. And Descartes walks away with inertia and a few other things. And only later does Beekman, after he dies, does Beekman's son publish his journals. And we find out that Descartes swiped half his physics from Beekman. Tales from the crypt. The fun part is to find out things like Galileo had 3 illegitimate children, never got married. Newton might have been gay, never married. That stuff, that Newton was a nasty character, that stuff takes 10 times more research to find out than the physics. The physics is there. But if you want to find out who is a mean, nasty character, you got to read their letters. And Newton fought with everybody, fought with Hooke, Flamsteed, everybody who had a Hooke, my God, what he carried on with Hooke. But that's another talk.
Well, thank you. I can see you've got quite a number of talks in you. So maybe we'll be calling you back. I see there's a lot of thanks to you in the chat window, so you should be sure to look at the kind compliments. And yeah.
Where do I find them?
In
so
the
if chat
you
window.
Have a page showing, you go to chat instead.
I will read them later.
Okay. And I do want to thank everyone for coming out to spend a little bit of time together. This is a lovely use of the new community space at AAPT. And I
thank you.
Especially want to thank Jean for your really charming presentation. I don't know how many microphones are on to hear the applause, but you just have to know that it's there virtually. And with that, I think we're all set. Mike, is there anything else we need to say? There's another one of these coming up shortly.
Yeah, we're going to try to do this once a month, roughly. So the next author series event is November 9th at same time, 7 o'clock Eastern, and the host will be Rebecca Vieira, who is the author of the, I think, 3 different books under the series title Teaching High School Physics. So Rebecca will host that event, and it's November 9th at 7 o'clock. But thank you so much for everybody for coming to this. This is great. And thank you, Jim.
All.